So for this homework, we started with a problem about thermal conductivity. So we have a heat source, which is 25 watts, but we have to divide that by 2 because it's being propagated through both, through a symmetrical sheet. It has a given cross-sectional area, a given thickness, and a given temperature difference. And from that, we're able to calculate the K value of this material, which turns out to be about 0.8. For this problem, we have a pipe that is quite hot, 280 degrees Fahrenheit, and it's propagating heat into the environment. So we have to find the surface area, the change in temperature divided by the change in distance, and then we know this value of 6 BTU per hour feet squared degrees Fahrenheit. So from that, it's just plugging and chugging. We know that the cross-sectional area is equal to pi times the radius times the diameter, I should say, times the length of the cylinder, and then from that we can calculate the BTUs per hour, and then the amount of money it takes to supply that heat transfer. For this problem, it's about radiation in and radiation out, and we have to use both this absorptivity value and the emissivity value, which is 0.3. And kind of balance that. For these two conceptual problems, it's the driving force in heat transfer is temperature, in electrical current is voltage difference, in mass transfer or it's pressure difference or chemical potential or concentration gradient, and then these are just the values that are represented by the equation. Q is equal to negative K A delta, or D del T del X. And then the final problem is about the binary diffusion coefficients, which just have to do with this scale, which were mostly lookups, and then we had to also scale them by these values, by the atmospheric, or by the pressure differences, and then by the temperature differences if those were different.